So I am Francis, full-time research scholar from SRM IST, Kattanguluthu. I am doing my research under the guidance of Dr. P. Sambat, Associate Professor, Department of Mathematics, SRM IST, Kattanguluthu. This is my one of the paper. So entitled as Dynamic Model of MHT Bioconvective Hybrid Nanofluid Flow over a Cone and Plate Surface. So these are my outline. Introduction. First of all, we have to know about the heat and mass transfer. Actually, heat and mass transfer have a lot of applications, right? For example, we are sitting in the room, so we are using AC. This is some kind of heat transfer. For many applications, this contains heat and mass transfer, like using laptops, we are cooling systems. Like mass transfer have a lot of applications in real life. Okay. Next, bioconvections. Actually, convection is one kind of heat transfer. So heat transfers is happen due to convections and conductions and radiations. So convection is one kind of heat transfer. In particularly bioconvections. Actually, heat transfers is happening in the fluid. Which fluid is containing the microorganisms. It's called bioconvections. Bioconvections. So bioconvections is the phenomenon of convective fluid motions caused by biological organisms like bacteria, microorganisms and cells. And it has lot of applications in medical science. And these are some literature reviews. So actually in presentation purpose I give some literature reviews. Actually I provide full papers in manuscript. So this is our model. Actually I taken two geometries. One is cone and another one is vertical plate. Actually our novelty is we are investigating that we have a heated cone and plate. We are submerged into the fluid and we are investigating how the heat and mass transfer happening in the fluid. Actually the fluid containing microorganism we call as a bioconvection. So actually this is our geometry. Here omega is a half angle of the cone and r is the radius of the cone. And B naught is a MHT. So MHT is nothing but a magnetic field. So I am telling later why I am using magnetic field in this model. Next, in this model I am adding a nanoparticle. Actually, I am using hybrid nanofluid, hybrid nano method. I mean, I am combining the two particles into one base solution and one base fluid. So here, y-axis located at the perpendicular to the cone and plate, and x-axis along the surface of the cone and plate. So this layers as boundary layer. Actually, this full papers we are investigating and we are explaining the heat and mass transfer via boundary layer theory. Actually, boundary layer theory is one of the best method to investigating the heat and mass transfer. Actually, here I am considered two-dimensional and incompressible and steady flow over the vertical cone and plate. Here our fluid properties, all the fluid properties are constant except the density of the fluid. These are our governing equations and continuity equations and momentum equations and energy and concentration and microorganism equations corresponding on boundary conditions. Actually, I am taking here T is equal to T wall means actually the constant temperature. So this is the initial model. So we are taking the constant temperature. We further we can improve the convective boundary conditions and for etc. Actually, in continuity equation, I am using r power a equal into u. For actually a, if a is 0 means it's a vertical plate. If a is not equal to 0 means it's a vertical cone. Just slight difference. So we have a system of nonlinear coupled PD. Actually, we have to solve it. Okay, but reality we don't have any analytical method to solve to get an exact solution for this system of nonlinear coupled PD. So for the for the purpose we are going to numerical investigation. So this articles based on numerical investigation of heat and mass transfer. So for numerical investigation, I am converting the system of nonlinear coupled PD into system of nonlinear coupled ODE. Actually, I am familiar with ODE, so I am going for ODE. Okay, so we can solve in the PD into directly PD if I find a difference. So I am converting the PD into ODEs by the similarity transformations. So after the similarity transformation, we get the equation 7, 8, and 9, 10. These are all the converted equations for the governing equation. So corresponding boundary condition I mentioned in the equation for 11. So numerical investigation. In this method I am using Keller box finite difference scheme. So find Keller box method. Actually for Keller box method we have to convert the system of system of nonlinear coupled ODE into system of first order ODE. So actually the nonlinear we have to convert into first order. So after converting the first order, we apply in the finite difference scheme. So after applying the finite difference scheme, we have discovered the equation. So we have to linearize the equation. So after the linearization equation, linearize the finite difference scheme by the use of Newton's method, we have system of algebraic linear equations. So we can solve the system of algebraic equations by the Black elimination method, and a lot of methods are available. So I am using Black elimination method. So resultant discussions. So here I am using I'm taken some values of Actually these values are taken from the literature review. So this all the values are fixed unless it says otherwise. So this is our main concept of this paper. Actually we are using MST, right? MST means magnetic field. Actually why are we using the magnetic field in the paper means actually we are increasing the magnetic field. Just see a figure 2, the MST, I mean M means MST. So we are increasing the MST value, the velocity profile decreased. So the velocity profile will be decreased according to the Lorentz force. Actually Lorentz force what says that if you are applying the magnetic field perpendicular to the fluid, the velocity will be decreased. So according to that force we get the same result from this fluid flow. So this is a main part, heat transfer. Actually this pi 1. Actually pi 1 means it's a nanoparticle. Actually here we are using two kind of nanoparticles. One is silver, another one is titanium. So why I am taking this two nanoparticles at the same time? Because it's increase our heat transfer rate. Just see the graph. So you can see some layer should be go upside. That's mean thermal boundary layer thickness will be minimized. Actually the thermal boundary layer thickness minimized means heat transfer will be increased. That's the boundary layer concept. So boundary layer concept is, can say simply, we have to minimize the boundary layer thickness. If we minimize the boundary layer thickness means we get heat transfer faster. So according to that boundary layer concept, we are increasing the volume fraction of nanoparticle. We get a maximum heat transfer for this fluid flow. So as well as pi 2. Actually pi 1, pi 2 are two volume fraction because we are taking two nanoparticles and hybrid nanoparticle. Actually so numerical investigations. Oh, sir, okay, sir. Conclusions. So the conclusion is, so a lot of researchers has done the nanoparticles or give a high heat transfer rate. Here I am using hybrid nanofluid. So hybrid nanofluid gives a better result comparing the nanofluid. So while using the MST, we can get maximum heat transfer comparing normal fluid flow. Actually for MST we can give some examples. So for MRI scan we are using the MST. So MS is nothing but a magnetic field, right? Okay. So this is my reference. Thank you. Yes, sir. Actually, hybrid means we are taking two nanoparticles. Actually, nanofluids means that the fluid. Two types of nanoparticles. Actually, where nanofluid means the fluid containing nanoparticle, single nanoparticle, the one base fluid and one nanoparticle. Actually, hybrid means one base fluid but two nanoparticle. I mean, two nano kind of two types of nanoparticle. That's why we call it hybrid. Sir, I'm not mentioning this slide, sir.
What is the difference between Newtonian and non-Newtonian?
Newton's is obey the Newton's law of viscosity. So simply say Newtonian fluid is a water, sir. Non-Newtonian is a paste, kind of paste. So paste is also fluid, but it's a thick fluid. So actually, here I'm taking constant boundary condition, but in manuscript I provide full paper. For presentation purpose, so you were asking non-dimensional boundary condition, dimensional. Actually, it's a dimensional. Equation 6 the dimensional boundary condition. Equation 11 is the non-dimensional.
What does it mean by y?
Y is y-axis. Y tends to infinity means it's outside the boundary line, not a real infinity. Actually, the outside the boundary line. Inside the boundary line only heat transfer, one mass transfer will happen. Outside the boundary line, it's normal to the flow.
So you are using some transformation.
Yes, sir. Similarity transform. Yes, sir. Similarity transformation.
When you are applying this type of transformation, what type of transformation you are using? Or you are getting all
Yes, sir. It's some error, sir. Error means right 0.01 error will occur, sir, because it's 0.01.
0.01 error occurs.
Yes, sir.
How can you make it?
Sorry, sir.
How can you make it? You are converting your PD to OD. Right?
Yes, sir. Actually, the solving the PD into directly in PD means we get better solution. If we solve the PDU and transform the OD after applying the fine difference means it has some error occurs, sir. For the transformation purpose, there is no error, sir. Actually, I am telling the numerical investigation, sir.
When you are applying the transformation, then what type of information you are using?
Actually, okay, sir, I am understand the question, sir. But
If it is not answer will be it is also okay. But find out.
okay, sir.
Because when we are applying some transformation, converting to OD. So obviously some information we are using.
Yes, sir. Of course.
We use infinite number of systems. Yes.
Sorry, sir.
In case of PD, we
Yeah.
have infinite number of systems.
No, sir. So, final number of sir.
How?
Not infinite, sir.
How?
Sorry, sir.
Like you can partial condition.
Yes, yes, I can consider.
But
It's infinite.
particular condition is a particular.
Actually, for PD, sir, there's an infinite solution,
Any
sir.
other question from participants? Go to geometry of economics.
Yes, sir.
So your y, your horizontal axis is y.
Yes, sir. Actually, y-axis is located perpendicular to the flow, sir. Simply.
So flow is perpendicular to the
Y-axis is the perpendicular to the cone and plate, sir. X-axis is the surface of the cone and plate, sir. Along the cone and plate, sir.
go to boundary condition when whether these two matches are
Yes, sir.
T and y tends to infinity.
Yes, sir. Actually, y tends to
Go
infinity.
back to geometry.
Actually, y tends to infinity means it's outside the boundary layer.
See,
Actually, you are asking this y is slanting to the Actually, that's not a problem. Actually, I'm.
That's not a problem.
Actually, actually, from equation 7, so we have cos omega. Actually, if omega is 0 means it's a plate. So actually the so, okay, sir. I'm telling, sir. Yes, sir. Yes, sir. Lost the micro.
Fluid flow, it is in which direction?
Actually, fluid flow is up direction, sir.
That is the excited now.
Yes, sir.
But you have taken extension.
Why tends to increase?
Why tends to increase you have taken?
Actually, fluid flow in the upside means boundary layer is happening in the y-axis, sir. Actually, the flow is the fluid flowing to the x-axis, sir. We just showing the one object in the fluid flow. Actually, the fluid, the boundary layer forming the top of the object, sir, not x-axis, sir.
So, go to equation.
Yes, sir.
You considered MHT, right?
Yes, sir.
That is the
Yeah,
term
sigma.
that involves magnetic
B naught square, sir. Yeah. B naught sigma 1 B naught square.
B naught square.
Yes, sir.
One last question.
Okay, sir.
How you can say, in simple and brief, by the explain, how you can say your research problem is innovative analysis? In abstract sense, you can.
Yeah, okay, sir. Okay, sir.
Equations and all.
Oh, okay, sir. So, in reality, we are using inverter, right? Inverter in every home. For inverter, we are using distilled water for some period of time, right, sir? Actually, distilled water is costly. So, in last research, we are only working on the pure water only. So, in my problem is the water containing microorganism is the cheapest one comparing the distilled water. Simple, sir.
Then what kind of solution you are using in such case?
Such case, use this kind of nanofluids to get cost wise better, yes, sir.
So I put something different. Actually this is dark blue, sir. This one is not visible correctly here. Yeah. So good evening everyone once again. So I am Mohan Rasu SS. I am PhD research scholar and I am doing my research under the guidance of Dr. R. Rakiyappan, Assistant Professor, Department of Mathematics, Bharatiya University. So here I am going to present my paper titled Finite Time Stability and Finite Time Contractive Stability for Fractional Order Neural Networks with Impulsive Adaptive Control. This is the plan of my presentation. So first we will see some introduction related to the finite time and fractional things. Actually, the notion finite time stability was introduced in 1950s in Russian literatures. It emerged after the translation of Russian literature to English in 1960s. After that, many results are derived related to finite time stability, and actually this concept was further developed as finite time contractive stability, where they incorporated the property contractive stability into this. And fractional calculus have been used in many places, and fractional more than integer order. In some places, fractional calculus gives more natural way to represent the model, and they work better than the integer order models. So there are many results developed for fractional order models. This is the definition for finite time stability. I am taking the general time delay system. So this is the mathematical definition for finite time stability. Given three constants t, C1 and C2 with C2 greater than C1, my system 1 is said to be finite time stable with respect to this constants if the initial time phi less than C1 implies that x of t less than C2 for all t belongs to closed interval 0 comma t. So we will see more about this, and similar to that we define the finite time contractive stability. We add one more condition to the finite time contractive stability. So this is a simple pictorial diagram for FTS and FTCS. So the first x0 is the initial value. So what I am saying is, given that initial condition stays within a bound, my dynamical system always stays within a certain bound, considering up to a certain time period. So the small, in the first figure, the small circle denotes the bound for my initial condition, whereas the big round denotes the initial bound for my entire system. So if the system stays over a finite period in this bound, my system is said to be finite time stable. Whereas in FTCS, a contraction can be possible. Like if I am taking x0 in that second round circle, then the system may go up to as much as possible the outer circle. That is a bound for general. Whereas over a finite period of time, it should the bound is contracting. So the inner circle. Actually, the main aim is we are considering it up to a finite time. There are more stability conditions. There are more stability related to asymptotically stable some things, but this is in this we are considering only for finite time period. So this is, I am taking the general neural network model. So this is my model. I am taking impulsive adaptive control. So this is the model definition. So this is how I update the adaptive gain matrix. I am using adaptive impulsive control. So control is used to attain some stability in neural networks. So this is the results I obtained. I use Lyapunov function to derive these conditions. If the given system satisfies these 5 conditions, my system is said to be finite time stable with respect to the constants C1, C2 and T. Whereas if I add one more condition, 6, my system is said to be finite time contractive stable. So with the numerical examples, I am taking the values which satisfy the theorem, and when I simulate the results, I plotted the graph. So we can see that after a certain time period, my results are going into a stable manner. So this is my obtained results. These are some references. Yeah, that's it. Yeah, yes sir. Here I am not considering any physical meaning, sir. Yes sir. Sorry sir, actually I am not considering any physical meanings here, sir. So yeah, my aim is to attain stability here, sir.
What sir is asking now, first, can you define what do you mean by neural network here? And then what do you mean by fractional order neural network?
Yeah, so neural networks is a mathematical model for brain neurons with the help of differential equations. Whereas here we use fractional order neural networks, which means we use fractional derivatives. This is a more generalized version of differential equation, integer order differential equation. In some places, this gives more representation over an integer model. It has some advantages. Yeah, okay, sir. Yeah. Okay, sir. Okay. Okay, sir, thank you.
You have shown some numerical examples at the slide of
Yeah, yes, sir.
how you have taken these values random or any limitations? Because, for example, suppose you take temperature under this value, you cannot take more than
Yeah.
probability value. So any limitations you have for these values are taken very randomly because all the values are available in your hand, you have taken this way.
No, sir. Actually, the main objective of this study is to find the conditions for stability, find time stability, find time constant stability. So I can take the values in random, but the value should satisfy this theorem. So this is the theorem I am obtained.
What I am asking is, for example, human height is maximum 7 feet.
Yeah, yes, sir.
Numerical, suppose h is height, that h value you can take 10 also.
Yeah,
But it is physically not fixed.
yes, sir.
Understand my
Yeah.
point? Okay.
Hmm.
Suppose one equation is defined for height. Mathematically, that equation height you can take 10 also. 10 means it's possible.
No.
10 feet.
Yeah,
So like this, there are some values. So numerically and mathematically, you can take any value. You can solve it. But physically not possible. That are called limitations.
yes, sir.
We have such kind of limitations in this parameters.
Actually, here there is no limitations here, sir. We can take any real numbers. We can see that D is a diagonal matrix.
Suppose you take any real number 1 crore, then in that case, the physical model will it be defined?
Yes, sir. We can see that we are considering from R power n cross m, so it can be meaningful, sir. So depends on the situation, sir. This is a general model. It may take any value, sir.
Suppose you take electrical network, I will give you one more example. Maximum capacity of the power, 10,000.
No, sir. Sir, what I am saying is, so this is a general model, so this can in general take any value, sir. So if I am going to any particular value, so it should be.
What I am saying is that model that should follow natural physical phenomena.
Yes, sir.
It is not violate.
Yes.
Correct?
Yes, sir.
Everything we are doing, we are formulating or writing literature that is with respect to what? With respect to some physical phenomena.
Yes, sir.
We should
Yes.
not violate it.
Yes, sir.
If you violate that, it is not a right research paper.
Yes, sir.
Okay. So, if you follow like that, what are the limitations of parameters in this? Simply are telling you can take any value, not like that. Numbers are available
Okay,
from
so I will
So-
raise a further question. Go to numerical example.
This one.
Here, you have taken D as a diagonal matrix, right?
Yes, sir.
Why not you take some super triangular matrix? What happens to your network?
So, actually, this is how the model is defined, sir.
Is there any specific reason why you have taken that as a diagonal matrix?
Yes, sir. Actually, this model is a more number of neurons are there. So, if I suppose that x is a vector, so if I have x1 and x2, if I multiply it with the diagonal matrix, I will be getting some d1 x1 of t, d2 x1 of t. It will be separate neurons, sir. So this is a generalized version with multiple number of neurons. For numerical simulations, I am only taking where neurons are 2. So this is a compact form representation.
The weight matrix, right?
Yes, sir. Wait for that F.
Is the weight for your neurons, right?
Wait for activation function, sir. Yeah.
Weight for activation function.
Yeah.
What activation function you use?
I used to tan, sir. Tan H.
Tan or tan H?
Tan H.
Yeah.
Tan H.
Cannot
Yeah.
activation function.
Yes, sir.
Only tan H.
Tan H.
Why tan H?
I don't know exactly, sir, but I think tan will tend to infinity.
No tan. Don't talk about tan.
Okay.
Tan is different from tan H.
Yeah, actually, tan H will lie inside some limit. I think so. I don't know, sir, but
Because whatever number you will give, tan H activation function will shrink the domain.
yeah, into S-shaped curve. Yeah.
1 to 1. That's it. That is the reason for. If you give any bigger number, your tan H activation function will reduce the number between -1 to 1.
Yes, sir.
Clear?
Yeah. Yes, sir.
That's why you can get the stability.
Okay, sir.
And others, what language you use to simulation?
MATLAB, sir.
MATLAB.
Yeah.
Try with some other activation function like sigmoid.
Okay, sir.
Or relu or some other activation function. See what happens.
Okay, sir.
Right?
Okay. Thank you. Thank you so much, sir. Thank you for your suggestions. So actually, stability is given that my initial condition is within a bound. Whenever over a finite period of time, my dynamical system stays within the bound. This is finite time stability. Whereas in contractive stability, my at the end of that particular finite time, that bound may decrease, contract after some period. So I am adding some in between time. Up to this time, it should be within a bound. After that time, it is contracting. Yeah. Thank you, sir. Thank you so much, sir.
Good evening, one and all present here. The title is Forecasting Air Pollutants with Dynamic Mode Decomposition. I am Aditya, PhD Research Scholar, under the guidance of Dr. R. Rakyapan, Department of Mathematics, Bhagar University. This is the plan of my presentation, and I want to begin with the ideology of this presentation, that is about air pollution. Reducing air pollution is of paramount importance for a multitude of reasons, ranging from safeguarding human health to preserving the environment and ensuring a sustainable future. The air pollution got its severity by increase in the amount of air pollutants that have been imposing into the whole atmosphere. So, in order to effectively reduce air pollution, it's important to predict how the air pollution levels might arise. The method I have chosen is dynamic mode decomposition. It is a data-driven algorithm, and it is known to be a future prediction, factorization and dimensionality reduction technique for data sequence. So this is the definition of dynamic mode decomposition. We are considering our data set as tall skinny columns of the matrix named X, and with the initial condition and xk, and xk is stepped to xk plus 1. That's where our future prediction begins. So here, as we can see, xm is the future data that may arise by constructing a data matrix X prime. This can be done by propagator matrix A that maps X to X prime. So DMD has attracted a lot of researchers. As a result, it can be applied to many various fields, and a few of them are listed here. So this is my methodology. First of all, we have to convert our time series data to a multidimensional series of size R cross S as row and columns. In this way, the time series is decomposed into a Hankel matrix which is of this form, and apart from that, dynamic mode decomposition has a strong connection with the Arnoldi algorithm. That is, our dataset matrix can be generated by the propagator matrix A and the initial condition x1, and here it looks like. So this is the main part of algorithm. In order to decompose my data set, I am decomposing it with singular value decomposition, and for the propagator matrix A, since it is computationally very large, so we are taking a reduced rank matrix A tilde and proceeding in this way and making the spectral decomposition of A tildes, we can construct the XDMD matrix which is of this form. So, the data considered here is the effect of air pollutants in Delhi from January 2013 to March 2023, and for prediction an addition of 18 months is provided, and 2.5, 10, nitric oxide, nitrogen dioxide, nitrogen oxides, sulfur dioxide, carbon monoxide and benzene are the data I have collected for the forecasting. So, these are the result I obtained. This is the performance metrics table, and measurement of model performance is based on root mean squared error and mean average error, and for additionally even though there will be some considerable change in atmosphere during COVID-19 lockdown, DMD proves itself as a good predictor and estimator of dynamics for a given set of raw data. So, the future direction will include some effective comparison of dynamic mode decomposition with some standard conservative methods, and these are all the references I have gone through. Thank you.
What do you mean by the dynamic mode decomposition?
Dynamic mode.
Why it is dynamic?
Sir?
Why it is dynamic?
It is a data driven method, and it can be applied to a differential equation which is dynamic. So, dynamic mode decomposition.
Okay. And in case of pollutants, what type of pollutants you are taking?
Some of the major air pollutants. These are all the pollutants I have considered.
These data are generally available?
Sir?
Are you taking some data?
Somewhere you got a data set, that is what professor is asking.
Sir, central board data collection.
From?
Central board.
Central board, right?
Okay, you go to graphs.
Fonts may be a little bit large, it's not visible there. You are showing this like.
Yeah, so you applied the singular value decomposition, right?
No, sir. This methodology I have included singular value decomposition.
Yeah, somewhere you applied singular value decomposition. Go to the next slide. Here for x, you applied a singular value decomposition.
Yeah.
Right? And you considered only u here. Right?
Sir,
You considered only u here in your solution. But whenever you are doing a singular value decomposition, you need to concentrate on sigma that matrix. That x needs to be a rectangular matrix, and the sigma and the x should be of same order. That is the condition for singular value decomposition.
Sir, for eigen decomposition, the matrix should be a rectangular matrix. But singular value decomposition can be applied to any kind of matrix.
Yeah, any kind of matrix. Even we can apply for rectangular matrix also. But what can you say about U and V star here? You have taken only U, right?
Yes, sir.
See equation number 6.
I am decomposing my data matrix S with the
Okay, what language you applied?
Python.
Python. So what is the dataset size?
From January 2003
No, dataset size.
Training set, data set, size.
You took 80% of dataset is you took for training, right? I am asking dataset size.
I can't remember exactly.
Then how you applied Python? You need to upload dataset, right? Have you uploaded? Have you implemented in Python?
I can't remember exactly the size.
So you told clearly that statement taking 80% for the test and 20% for the prediction. For the test you done using I think Python, right?
Python.
Then data set size should be there, some quantity. Okay, check it later. And
Yes.
you go to the title of your work. I have one general question right now. This is forecasting air pollutants with dynamic mode decomposition, right? The question is, for this model, how you can say that SVD is suitable?
Sir, SVD is for dimensionality reduction purpose. So after applying the dimensionality reduction technique, specifically as SVD, using DMD, I am forecasting the air pollutants. So DMD plays a binary role, like it is used for dimensionality reduction as well as future prediction. So SVD is not applicable for I think future prediction.
Not future and present, that you leave it for your problem, for your analysis, how that singular value decomposition is suitable to this problem. Because whenever you select any method to any problem, that suitability should be there. If it is not suitable, we cannot take it. So how you can link that singular value decomposition problem with this problem?
First of all, after collecting data, I am reducing the dimensionality using singular value decomposition, and I applied dynamic mode decomposition.
No, how you have applied, that is I am not asking. Why you apply?
So for hand.
Understand my question? I am not asking how you have applied. Why you apply?
To
If you want to capture the important information, you can apply SVD.
Okay, try to find it. Whenever you are applying any method, what is the objective of that method in that particular problem? That you should try to know it first, so that you will have the clarity in the concept wherever you are doing, right?
Sir, first of all, after collecting data, dealing with the high dimensional may be a burden, computationally burden. So I am reducing the dimensionality using singular value decomposition.
Okay, that's right.
Do you know any other method other than SVD for dimensionality reduction?
Proper orthogonal decomposition.
Okay.
Just now I am studying about it.
You can apply principal component analysis.
PCA.
Right? You can apply principal component analysis, and you can apply SVM method also. Yes, you can apply support vector mission also, because you are relating with the time series, right?
Yeah.
Whether that series data is transient data or non-transient, you can choose. Clear? Okay.
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 Thank you.